vi skulle hatt med Johann fra VX i person. Minutter, og snakke om litt hvorfor vi skal teste, hvor vi kan teste, og eventuelt resultater vi kan få av det. Vi kan ta imot spørsmål via YouTube-chatten underveis, men vi kommer til å besvare de på slutten. Og det meste kommer til å foregå på engelsk. Johann kommer til å gå gjennom en presentasjon med litt live demo av testinstrumentene. Og de som ønsker litt ekstra oppfølging, forslag og hjelp til løsninger i ettertid, kan ta kontakt med oss. Det vil jo også følge opp deltakerne ettertid selv også. Så da gir jeg ordet over til Johann Draxelmayer hos VX, han kan også presentere seg selv. Vær så god, Johann.
So it's my turn?
Yes.
Alrighty. Good afternoon, everybody. My name is Johann Draxelmayer. I will hopefully guide you through the next 40-45 minutes on why it might be a good idea to put some meters on your Ethernet links and verify performance of those. And I work with VX for the last 16 years, first as their distributor in Germany and then in Austria. And now I'm also helping them managing the sales channel in Northern and Central Europe. And please allow me to spend the first 2 or 3 minutes on 2 slides that I've prepared for you guys, talking a little bit about VX. We are basically a company founded in the Silicon Valley in 2006 by a handful of people that had been in the industry by then already for many, many years. And we are a privately owned company. We are financially independent, and we're pretty proud that we've been profitable basically from the second year on since introduction. We are very focused on basically communications, services, assurance. So we help basically in troubleshooting. We help with installation processes, with diagnostics. We also have an offering for proactive monitoring, both on the fiber side as well as on the Ethernet side. We try to be customer-centric, so that means all the sales guys like me and the channel, we're out there listening to you, to your problems, and trying to come up with basically solution-oriented culture in terms of that the products that we develop try to be like focusing on those main purposes that the sales and marketing brings back from the field. Typically, we design, we manufacture, and we produce all our instruments ourselves in our factory that we own. And our focus is on the one side portables for field use for all the installation teams that are out there bringing up services, and that goes all the way into the core of the network, where we offer centralized rack mount test heads that can be tested against from the field force. Our headquarter is in Fremont, California, and our founders, they are initially all from there, so it was very important for them, despite traffic and all the other stuff that you may focus or face in the Silicon Valley. They really want to have our headquarters still there for early access to all the leading technologies. On the second slide, this is just to basically show you where it all started in 2006 when we introduced the MX100 which was our very, very first single port 1 gig copper and fiber test set. As I said, all it did was basically Ethernet. And over the last 16 years, we have basically, first due to natural growth, new products, and also acquisitions, have we developed into a full sortiment manufacturer of test and measurement equipment, not only in the fields of Ethernet as of today, but also in the fields of fiber optic, transport, test equipment. Talking about OTN is the big topic there, optical transport networks, XWDM, and on the other hand, then cable TV and fiber optic test equipment. So what you can see here is that we have constantly, established and developed new platforms for testing as the requirements have basically changed from standard 1 gig Ethernet testing through 10 gig and then 40 gig into 100 gig, where we are at 400 gig right now being deployed in the core networks today. So why would you test? Roger and I, we've had many discussions about this. Why would you want to spend time, money, and effort to test your Ethernet services? Well, the first and most important reason for that is that typically, if you are in a business environment, so what's called a service level agreement is signed, and a service level agreement typically defines what you get for your dollar. So, in other words, let's assume you're a professional customer and you need some services between a variety of cities where you have your offices, where you have your data centers. So what you buy from the carrier is basically a service to transport data from one location to the other. And defining how that service works for you is, first of all, you need to know how much bandwidth you want to basically be able to transport from A to B and from B to A, and how do you define that bandwidth. You also want to know how much error, how much room for error is there, and what does that mean in terms of you as a client. And if there's packet loss, how does your application, how do your apps, how does your software, how do your servers react to that, and how can you verify that? Two other measures that are related together are delay and jitter. Both are also important to be verified on your network, on your Ethernet link. And it is important for you to know how much delay can your applications digest, how long will they still work properly, what do you need to put into your SLA in terms of millisecond round-trip delay so that your applications still perform properly. What we keep seeing in the 1G, 10G, less in the 100G markets is that customers just fix their issues with ever more bandwidth. So personally, I've been involved in a really interesting case where a customer got basically a 100 megabit DSL subscriber line, and all they wanted to do was get 10 voice over IP telephones in service, and it just would not work properly, and the resolution was to just upgrade from 100 meg to a 200 meg, and then the problems went away. But at the end of the day, that is not what you can do like all day long, and you cannot always kind of push more bandwidth towards the customer. First of all, the average bandwidth is rising dramatically and very quickly, so that's getting ever more difficult, and really a stable, good and verified service level agreement is just what you need at the end of the day. The second thing is, if you're in the installer in the installer market, is a proof of bring up. So typically what you have to do is, if you're working for a large carrier and you do some bring up for them in terms of services, you must give the carrier or the end user a protocol that you have verified that what he's paying for is what the link and the service, basically the services that are working on the link can basically perform as it is on the paper. And last but not least, a proof of equipment performance. This is relevant when you start deploying new devices into your network. Although the manufacturer typically gives you a piece of paper where you can see what kind of performance the switch, the router, whatsoever is supposed to do. Many large carriers have their own labs and they run their own tests, especially when it comes to IPv6 versus IPv4. What's the performance on each? When you mix the two, what is the performance, the overall performance of the equipment? And there is still a lot of surprises in that area. So another reason, and this is basically when it comes to finger pointing in large networks of multinational companies, the finger pointing between the server or infrastructure guys and the networking guys. So I consider myself being a networking guy from the past, and we had the big saying, "It never is the network," and we were always sticking to it. The question is really, how can you prove that? And many of you probably are in that environment every day, where there's finger pointing between the colleagues from the IP department and the guys that have deployed the network, whether it is an issue on a server, whether it is an issue on the application on the client, whether it is the client itself, or whether it is the network. So again, we stick to it never is the network, but how do we prove that? Well, all you can do is testing, and the testing actually can be complex. However, a big advice that everybody here at VX gives to all our customers: run your performance verification, what we call bottom up, which means we start at the lowest possible layer, which is the layer 0, as I call it. And what that means is check that all your cables are okay, check that your transceivers are okay, check that there is light on your transceiver, check that there's power on your copper ports, so that really the cable faults and the port mismatches and all the super trivial errors that you may run into every day have been sorted out. And once that is considered okay, you can start testing and run the service tests that are required. And another thing that comes basically from my history: if somebody comes up with his laptop and say, "Hey, let's do a ping and let's see whether we can ping that IP address," that has nothing to do with service verification for a variety of reasons, and you should not allow that, and you should do some real testing. So what does that mean? I mean, where do we test? Ethernet, as of today in 2022, really is everywhere, and you can see here basically a very, very, very abstract layer of how testing can be performed. Typically, you have field force in the field with portable meters. They can be more or less complex, and your testing applications can be either inside a data center, they can be between data centers, they can be from a data center through a carrier network that is managed to another data center. Your test examples can also include what we would then call the internet. So stuff where you don't really have any hands-on, that you could manage something, so you take what you get. And the testing can be performed basically from either a portable to a portable, so a point-to-point testing. You can run end-to-end verification of services. You can also run against a loop on the remote end and run some tests. And what more and more large organizations and also carriers are starting to do is they start deploying centralized test devices inside their NOCs or their data centers. And those devices typically are twofold, like the box here on the lower end, that is basically symbolic for stateless testing, where you either run standard throughput tests, end-to-end terminated end-to-end tests, or you run against the loop, or you run a test that is called a Y.1564, and I'll talk about that a little bit later. And also, is there more and more deployment of iPerf servers so that you can basically test against the RFC 6349, which I will also talk a little bit later about. So the traditional way of testing, how did everything start? Well, in the old days, and since I don't know sort of the average age of the attendee here, I'm 53, so when I started into this business, we were at like 10 meg Ethernet with coax connectors, and there was still plenty of TDM in the world. So we had all sorts of E1s and E3s and DS3s and all this kind of stuff. And the bit error rate test, the good old BERT, was basically what you were performing when there was an issue. So you connected your test set and you started your bit error rate test, and after an hour or so you checked how many bits were in error, how many were good, and then you could basically make an assumption on what the quality of your link was. However, with the introduction of Ethernet, with all the packet-related issues that we were seeing from the beginning, and the much less reliable service that the early Ethernet links were providing, the BERT was not really suitable for, as I've written here, for assessing overall performance of a network, or a service was not even discussed at the time. So what today is being used in the stateless world, which means like the fire and forget world. You only want to basically test the performance of your network or the services running on your network is three well-defined tests. It is the throughput test, standard throughput test, with a lot of additional information that you can get from there, and I will show you basically a live example a little bit later in this webinar. The throughput gives you basically good statistics on a packet or frame level for committed interface rate, which is like how many megabits or gigabits per second you can transport over your link. It gives you a very good indication on frame loss, on delay, on jitter, on supposedly out of sequence packets, and so on. And it also helps you with service disruption measurements. So when you are on fail-safe links, you typically are required to prove that when the line A basically goes in error because there is a problem on that side, that the backup mechanism jumps in a certain amount of time, and that time you need to measure and you need to prove that the backup switching between the A and the B side is properly executed. Then the first test that got verified got developed by the RFC 2544, I should say defined by the RFC 2544, was really a test suite for benchmarking switches. So that RFC 2544 was never intended to be used for field testing, but because there was nothing else, and this was the only standardized Ethernet benchmarking at the time, it got more and more and more misused to be used also for verifying services being transported on the various Ethernet links, and really took, I guess, probably a decade. Almost a decade maybe, until the ITUT finally got together and started a program in the Y.1564, which is called the SAM, the Service Activation Methodology, and that really was the first attempt, and that's already more than 10 years ago now that started. That was the first attempt to basically allow end users or installer teams to have a well-defined test suite available that would give you all the KPIs that you already knew from your standard throughput testing, and put that together in a way that kind of, getting rid of all the shortcomings of the RFC 2544 that you were seeing when you were deploying services on the Ethernet. So what does that mean? The ITUT, the 1564, is an out-of-service test methodology, which means you can only use that when there is no customer traffic on your link at the time of testing. And as I mentioned, it's called the Service Activation Test Methodology, the SAM. And the Y.1564 really tries to solve all the deficiencies of the RFC 2544. What are the main benefits to the user of a Y.1564 over an RFC 2544? First of all, and that is where the money is that the total test time typically is dramatically reduced. What that means is that you can basically run more services testing at the same time, or the same time of testing in less time overall. And why that is, I will show you in a second. And also, with a big problem that our industry sees is, I guess everybody has a lot of problem in hiring new talent. So more and more things are getting sourced out, and while the RFC 2544 as a test result really gave you a lot of numbers that you had to do something with, the Y.1564 can basically be set in a way that you get a very simple pass and fail indication in red and in green, whether your service has passed what it is supposed to do or not. So this can also be run by, let's say, not so well educated people in the field, and at the end of the day, the time reduction. So you get in an 8-hour workday, when the truck rolls, you can get more tickets done with testing on the Y.1564 than the RFC 2544, and the pass-fail basically helps the people that are out there saying, okay, this is good, dear customer, give me your signature, and off to the next ticket. So differences between the 2544 and the Y.1564, really the objective of the test per se on the RFC 2544 always was device performance. Why was it device performance? Because it was very early in the market, and at that time, every switch that you bought, you really wanted to check, can it really do line rate with like short packets, or is there issues when I load all the switch ports with short packets at one time? Can the backplane digest all the traffic that is coming along? That is in the past. So really, when you buy a 10 gig switch, nobody questions whether it can do line rate on all ports or not in both directions, although sometimes there are still surprises. Again, IPv4, IPv6 on big routers can still be an issue, but technically that's all good. While the Y.1564, its objective, it really is the network service activation and then verification. So it does not even know about any like products that are in the middle anymore. It only knows, okay, there's a port and there's a service supposed to go to that port, and then there's another port on the remote side, and there's basically the termination point for that service, and I want to verify end to end, is the service that I pay money for performing the defined way. So the service validation is very different, because on the old RFC it was one service at a time, and when I talk service, it basically is an Ethernet stream that is going through the network, while the Y.1564 allows multiple services to be tested simultaneously once the configuration test is done. So in the performance test, the validation can be over multiple services at the same time with different test patterns. Throughput is verified on both. Latency is verified on both. Frame loss is verified on both, and also burstability. These are really the four basic tests. Packet jitter. There have been additions to the RFC 2544 on some test equipment that you can run jitter testing on the RFC 2544 as well. But it is also standard on the 1564. But basically, the RFC always was a single stream test, and it basically gave you one packet size after another. And I can show you then on the live demo how this is being set up, and why, especially when there is an issue with your service, the test duration is very long. Not only, as it's mentioned here, because it's a serialized test procedure. That is one reason, but the other problem is that when there's an issue, it basically, the RFC 2544 was developed to give you a performance limit in terms of a number, while the test result for the Y.1564 really is in relation to your service level agreement. So you define upfront what is good and what is bad, and based on that, you get a simple, fast pass or fail indication that the link is performing. So, how is a service defined inside an EVC, an Ethernet virtual connection? you basically have a physical interface that can go anywhere from even 10 meg still all the way up to 400 gig today. And inside that, basically that pipe, you can have a variety of services that are being defined, and you want to test them independently from each other, but at the same time, so that the accumulated bandwidth goes close to the limit of what your pipe basically is supposed to digest. A very, very important part, and this also belongs to the service level agreements here, is how do you define a service? And basically, when you remember the very first slide, we were talking about bandwidth. And the bandwidth profile, basically, you need to define two things. First, the bandwidth itself, and the standard talks about a committed information rate and an excess information rate. The committed information rate is either defined as a ULR or as an IR. And the ULR is basically the bandwidth that you see on the cable. So this is really relevant for you when you are the carrier or when you are the service provider, because this is where your limit is. If you have a 10 gigabit link, then 10 gig is the maximum ULR physically that you can transport. And a big problem, and let me show you that in a quick example here, is a misunderstanding. And what I'm doing here is I'm just switching to a box here in the lab that is connected to a 100 gig network. And all I do is I run a very simple 100 gig Ethernet test for you, just to show you in the test results why the differentiation between a ULR and an IR is so important. If you look here at the TX and the RX on the utilization, so you can see we are at 100% line rate, so this means this is 100 gig Ethernet. But the frame rate, depending on the frame size, which is basically the IR, the information rate, is only 92 gigabits per second, because you have an overhead on all your Ethernet packets, and the overhead really depends on the packet size. So while here we are running a test now, if we look at the setup in our traffic, we are looking at 256 bytes. So what we see, 256 bytes is the length, and at 256 bytes we lose approximately 7% of the performance between the utilized line rate and the information rate. And 7%, that's already quite a lot. But if you look at this, and there are so many like everyday examples of how this can lead to miscommunication, because the people that sell the service are talking about ULR, and the people that buy the service, they expect IR because they don't care about the overhead. But this needs to be defined up front, otherwise there's room for issues. If I change this to, let's say, 80 bytes, then the difference, and I say apply to all, and I say start, I say no, and now I run a test where you can see that my difference now is between 100 gig and 80 gig already. So really this is like 20% different. And when you use it, when you look at the data rate, this is down to 38%. So there's a lot of overhead compared to what you are just transporting in your data. So this is your data, basically the gray area. This is where you can use your own information that you want to transport, and the rest is being used by the network. There's an IP header, there may be VLAN tags or MPLS tags, there is a MAC header, there is a CRC. All that needs to be transported over the cable. So you really want to be sure that when you define bandwidth, you're very well aware that there's the different recognition of what bandwidth actually means in terms of whether it is on the cable, ULR, or whether it is IR, that is basically the plain information rate. So coming back to the slide deck here, the committed information rate is what you guarantee. The excess information rate is where you tell your customer, well, I'll try my best, but it's not my fault when we lose packets there. And then what the Y.1564, the ITU-T, did in that standard is they not only looked at basically the bandwidth, they also looked at buffers. And the buffers are defined by CBS and EBS. CBS meaning this is the committed burst size. EBS meaning this is the excess burst size. So that's the same as for the bandwidth, but basically in the other direction, in the Y direction, is how long can I send you data at line rate, which means how big a burst can every part that is involved in that link digest without dropping a packet. And with that, you have very well defined what you expect from your customer, or what you are trying to sell to your customer, just depending on which end of the or which side of the coin you basically are, whether you are the buyer or the seller. And in addition to that, and that's also the beauty compared to the RFC 2544, there is a service acceptance criteria. And that means that you can predefine what is good and what is bad. So you can define a frame transfer delay, FTD. That is basically what in the old days in the throughput and in the round trip in the RFC 2544 was defined as the round trip delay. So you go basically from A to B, the traffic is being looped back to you, and then you get basically a round trip delay, how long the packets take until they are back at its source. Then what's defined is the FDV, the frame delay variation. Frame delay variation basically is a modern word for jitter, for packet jitter. So you define that. Then there's a loss ratio, and there's an availability, which means how many packets am I supposed to lose, and for how many percent of the total active link the availability of the service is given. So to show you the committed and the excess information rate one more time, this is basically like a traffic light. So the green, the committed interface, committed information rate is basically the green area here, and there is guaranteed traffic no matter what. So there's no room for errors in that space here. And then on the yellow, you add the excess information rate to the committed information rate, and this is the non-guaranteed traffic. So you basically, maybe you allow 5 or 10% extra, and then you can still send traffic, but it is non-guaranteed for no packet loss or for the number of packet loss that is being defined. And then you have the red light traffic, so to speak, which needs to be the dropped traffic. So why is that important too? Well, if you are a carrier and your customer gives you money for 2 gigabits or for 5 gigabits, and you provide a 10 gigabit link, there physically, you want to make sure that for the money you get, you give the customer the fair amount that he pays for, and that the shaping actually jumps in when you are at a certain value here, where the red traffic, the drop traffic, is then really dropped. So when you think about a test result, when you have shaping in place, that means that you will very likely have packet loss in your test report, but still a pass, which means this has worked. So really here, from that moment on, from that line, from that top yellow bar on, there's no more traffic traversing through the network above that, because that is simply not allowed, and you shape it off properly. So this is for the definitions of basically that traffic light type CIR and EIR definitions. And then, as I mentioned that before, and here is here's basically the graphic to that. And the utilized line rate, the ULR, is what is on the cable. And the IR, the information rate, is basically when you subtract the interpacket gap, the preamble, and the start of frame delimiter. Then you get to the IR. So there is a certain difference, and the shorter the packets, the bigger the difference is going to get, because the IPG is ever getting longer. So the difference, the factor is basically less and less. And here is an example on a 100 megabit link. If you're going at 15-18 bytes, then your maximum information rate is at 98.7. So you could still argue probably in the field somewhere, okay, 1.3%, no worries. But when you go to 64 bytes, then the maximum information rate is only 76.2 megabits per second. So what that means is that there is a significant difference. And if your service level agreement, again, does not define well, is the information rate a utilized line rate, or is it an IR? Then you have a problem as the engineer, because sales and marketing, often they just tell, oh, we have this new 100 gig service. Perfect. Yeah, but 100 gig what? So it is very important, because this can, and I've seen this plenty times in the last 15 years, this can escalate very quickly, very, very high when customers spend a lot of money on interconnectivity and don't get the performance that they were expecting at the time. I see I need to hurry up a little bit because it's already 44. On the CBS, this is the same thing, committed burst size, excess burst size. So basically you have the guaranteed traffic and you add bursts that are a certain length. And the length is typically the committed burst size. So you guarantee, okay, you can give me line rate data for 20 kilobytes, 50 kilobytes, 100 kilobytes whatsoever. Then there is non-guaranteed traffic, and then the policing and shaping comes in again and drops off the traffic, hopefully properly. The service definitions, I have already talked about that, and I guess there is no need to go further into that unless you have questions about it. I'll certainly be happy to answer afterwards. And all that basically brings us to a test result on a SAM. And the most important thing on a good SAM in parentheses is your green pass here. So you can see the overall test passed well, the configuration test passed, and the performance test passed, and then you get a whole lot of numbers that this is then for the engineering that describe what you have measured and what for all the different services that you have tested at the same time, what was the frame loss count, what was the frame loss ratio, what was the frame delay variation, the minimum, the maximum, was there a lot of jitter, what was the availability, and so on. So this really is a very, very what's the English word for that? You can really stick to that. So when you have that result in your hand, there's not much room for argumentation. So if the service level agreement was defined well beforehand, and you show up with a VSAM test, with a Y1564 test at the end of the day, and they match, you just say, well, look, customer, this is what you pay for. This is what you get, and we have verified that for you. So there's a lot of safety for both sides because there is a well-defined, standardized test procedure for that. What's coming up more and more as well is, in addition to the stateless testing, many people are starting to ask about stateful testing, which means like TCP type testing on layer 3 and layer 4. Again, then there has been an RFC standard created, which is the 6349, that basically describes what you may know as the iPerf testing, when you had a laptop and a server blade, and they were both running iPerf, like some standard Linux software, and you could basically initiate a TCP session and run a test back and forward. That worked very well when the networks were like 10, 100, and maybe even 1 gig. But when 10 gig came along, and now at 40, 100, it's even more difficult to find servers, and also to find especially clients like notebooks or whatever that would have physically a 10 gig interface or a 40 gig interface. So what has happened is that the test and measurement equipment guys, they have implemented the RFC 6349, or in other words, they have implemented iPerf into hardware. So running that protocol, the TCP protocol, basically inside an FPGA, and allowing you to perform to establish several TCP sessions at the same time, allow you to do high-speed testing also on the layer 4, on the stateful side of things. However, you always need to be aware that in TCP, a lot of things can happen because there are very many rules for slow start and for window sizes. And when you test against iPerf servers, there's always an IP stack that is implemented in software, and that might be a good implementation or a not so good implementation. And test results do vary on 6349, and you need to be able to interpret the data and the results that you measure much better than it would be on a Y1564. So for us network guys, it never is the network. Y1564 on the stateless side really is, in my perspective and in my opinion, the non-plus-ultra in terms of Ethernet testing, while all the 6349, the TCP, and also what you may know as speed test, OCLA, really started with that. And if you go to the internet and you type speedtest.net from your notebook, you can do a quick verification of how much delay do you have to the next best server from OCLA, and how much upload and download do you get. That is all fine. all working very well on 100 meg, 1 gig, but on the higher speed networks, 10 gig, 40 gig, 100 gig, not 400 gig because there's no TCP testing on 400 gig right now, but that will come sooner or later probably. But all that speed test testing and so on, this has all been now implemented into hardware by the T&M people. So you have a reliable hardware-based box that does the same testing, but at the higher speeds than your laptop from home can potentially do. So what do you need for verification? And let's be serious. As I mentioned in, I think, slide number 3 or so, do it bottom up. So always start at the lowest possible level in terms of the ISO OC model. So make sure your cables are okay, make sure your transceivers are okay. And for the physical layer, I just can urge you, if you are involved with fiber optic links at 10 gig or higher, be clean. So try to have a fiber scope and some professional cleaning tools. And if your procurement guys tell you happily that they found now a cleaning tool for $2 instead of $5, that's the wrong way, because cleaning tools, there's a lot of stuff out there that shouldn't be. So make sure your cleaning tools are good and working properly. And at 100 gig and up, the rule of thumb is really inspect, clean, inspect, plug. So that is what you should consider when you're on 100 or a 400 gig link even, because dirt or dust there is your big enemy. Try to have a simple power meter. In the easiest way, you could use the power meters that just read information from the plugs inside the test sets. So this is a 4x25, and I can see my receive values, and I can also see my transmit values, and I can also see that my clocking is proper. So from a physical perspective, I'm good. And with that, a lot of potential issues like flaky cables, flaky transceivers, transceivers that are like really old or have gotten too hot at one time whatsoever, you can all sort that out with very, very, very simple testing. And get a visual fault locator. There's a 1 and 10 milliwatt versions available depending on how far you need to go. That really helps you dramatically when you are inside a data center and you want to find faults in your cable infrastructure. A visual fault locator can be of great help. For the stateless testing, a test set is always good that can run a throughput and more importantly a Y1564 test. Once during the installation the throughput test has shown okay, this is all good, so basic stuff is working. And yes, this is hard. If you need to do end-to-end verification, or even if you need a loop, you need to have a second box, a loop box, or a second tester for the remote end. And then if you go up to the stateful testing, you just get a more advanced test set that can run the RFC 6349 iCurve type testing as well. Make sure that this all works at line rate. So don't get fooled by advertisements. Try it out and connect it to a 10 gig server, at least run it as a client and check whether you can get the 10 gig or 9.8 gig when the delay is short enough upstream and downstream. And with that, I'm done. Thank you very much. And Roger, that would be back to you.
Thank you. We have one question, Johann. So, what is meant by the word burst stability in this area?
Burst stability?
That's the question.
We were talking about the committed burst size and the excess burst size. And this was basically this diagram here, where what you do is when you define a service, an Ethernet service, what you can do is, let's assume the service is a 200 megabit service or a 500 megabit service, and the physical interface is 1 gig. Then what you may allow the customer is that for a certain period of time or frames or memory, he can send you a burst at line rate for so and so many either frames or kilobytes per second. And that's how committed burst size is defined. So it describes the maximum number of consecutive frames sent at full line rate that the service can transmit and that are assured to be forwarded. So this is a question about memory, memory of the input ports of the clients when they basically enter the transport service.
Okay, thank you. Så jeg vil takke alle som har deltatt, og ta kontakt, så kan vi hjelpe dere med deres utfordringer. Vi vet at mange har bygd nett på forskjellige måter,